Have you ever just stopped and thought about how fast artificial intelligence went from, a sci-fi concept to something that's suddenly drafting legal briefs or diagnosing your x-rays?
Or running global supply chains.
Exactly. It's relentless. I mean, the pace is so overwhelming that the words themselves, AI, ML, LLM, Gen AI, feels like a whole other language.
It can feel like a linguistic shield, almost designed to keep people out.
Yes. We're just drowning in these acronyms, but we're starving for actual context.
And that feeling, that sense of being overwhelmed is exactly why we're doing this.
Mm-hmm.
For this deep dive, our whole mission is to get past the buzzwords and give you a really solid, grounded understanding of what artificial intelligence actually is.
Okay.
We're going to be digging into its conceptual DNA, really exploring the technical engines that make it run, and then analyzing its very real, very complex impact on society.
And we're drawing on a lot of sources for this one.
A huge range, from the philosophical origins back in the 1950s all the way up to, cutting-edge deep learning being used right now for fraud detection and drug discovery. The goal is for you to walk away from this feeling grounded and ready to actually engage with this stuff.
Okay, let's unpack this then, because to really get a handle on the scale of what's happening, I think we have to start at the very beginning.
The absolute origin point.
Right. We need to go back to the summer of 1956 to New Hampshire, and the moment the phrase artificial intelligence was, officially born.
That moment, the Dartmouth Summer Research Project on Artificial Intelligence was absolutely foundational. The field didn't just appear out of nowhere, of course.
Right.
In the early 50s, people were already talking about thinking machines, but under all these different kind of confusing names.
Like what?
You had cybernetics, automata theory, complex information processing. But in 1955, a mathematician at Dartmouth named John McCarthy realized that all these separate fields needed one unifying focus.
And he needed a name, a neutral name, that could hold this big new vision, which is where artificial intelligence comes from.
Exactly. The formal proposal for that 1956 workshop, it was written by McCarthy, Marvin Minsky, Nathaniel Rochester, and the great Claude Shannon.
Wow, that's a list.
It is. And McCarthy specifically chose artificial intelligence because it was neutral, it was ambitious. He wanted to avoid getting bogged down in narrow technical debates.
So he didn't want to get pigeonholed into just automata theory or something?
Precisely. And crucially, the sources suggest he really wanted to get out from under the powerful influence of Norbert Wiener, who was the central figure in cybernetics.
So AI wasn't just a catchy name. It was actually a strategic move to create a whole new academic field where they could set the rules and avoid the old intellectual battles.
It was a declaration of independence in a way.
So what was the central idea? What was the big world-changing conjecture in that original Dartmouth proposal?
It was revolutionary, really, in its simplicity and just how ambitious it was. The 1955 proposal laid down this core idea that still drives the whole field today.
Okay.
It says, and I'm paraphrasing here, the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it.
Wow. That's the ultimate blueprint, isn't it? The idea that if you can just articulate how intelligence works, if you can precisely describe it, a machine can copy it.
And what's wild is how forward-looking that proposal was. It outlined areas that are still the core of AI research.
Like what?
Natural language processing, neural networks, abstraction, even creativity. And the idea of machine being able to improve itself. The entire research agenda was basically set right there.
So the workshop itself, was it a huge success?
It's funny. By all counts, it was a bit disorganized. Only 3 people actually stayed for the whole 2 months. Ray Solomonoff, Minsky, and McCarthy. But it was the spark. It kicked off these crucial new directions.
It lit the fuse.
It absolutely lit the fuse. It led to the rise of symbolic methods, the focus on expert systems for limited domains, and it really sparked this ongoing debate between systems that use deduction versus those that use induction. It was the big bang for the whole field.
Okay, so we have the birth of the term and this foundational belief that you can simulate intelligence, but intelligence itself is such a slippery word, even for us. How do computer scientists try to organize all the different philosophical approaches to AI?
That's a great question, because a single definition is impossible. The standard framework, the one you'll see most often from researchers like Russell and Norvig, breaks AI down into 4 schools of thought.
And this is based on 2 different axes, right?
Exactly. The first axis is whether you're focused on thinking or acting. And the second is whether your goal is to be human-like or perfectly rational.
Which gives us the 4 definitions: thinking humanly, thinking rationally, acting humanly, and acting rationally.
Precisely. And you can group those into 2 big approaches. You have the human-centered approach, that's thinking and acting humanly, which is all about trying to replicate human performance mistakes and all.
And the other one?
That's the rationalist approach. So, thinking and acting rationally, that's focused on ideal performance, on doing the right thing given what you know. It's about logical perfection, which, humans aren't always great at.
The rationalist approach, that makes sense for, say, critical infrastructure. You want perfection. But the most famous test in AI history falls squarely in the other camp: acting humanly.
You mean the Turing test?
Alan Turing's test, yeah.
Absolutely. In 1950, Alan Turing proposed his imitation game, and he deliberately changed the question. He moved it away from the murky philosophical "can machines think?" to something you could actually measure. Can machinery show intelligent behavior?
The idea is so simple. You have a human interrogator typing messages to something behind a screen. If they can't reliably tell if it's a human or a machine, the machine passes.
And just to pass that simple test, a machine needs to master so much. It needs natural language processing to talk, knowledge representation to store what it knows, automated reasoning to draw conclusions.
And machine learning to adapt to new things.
Right. But Turing knew even then that just talking wasn't the whole picture. He envisioned something even harder. He called it the total Turing test.
What else does the total Turing test require?
It means the interrogator can see the system through a camera and can give it physical tasks to do.
Oh, wow. Okay.
So that adds 2 huge technological hurdles that most people forget about. First, computer vision, so the machine can see and understand the world around it. And second, robotics, so it can actually move and interact with things. We are still a long way from any AI passing the total Turing test.
That really shows how much bigger AI is than just, the chatbots we see today. But let's go back to those other definitions, the ones focused on thinking. Thinking humanly or rationally. Why is that approach so tricky for researchers and especially for, say, lawyers and regulators?
It really comes down to what Russell and Norvig called a philosophical impossibility. Defining AI based on thinking is basically unfalsifiable. You can't get inside someone's head, human or machine, to actually observe their thoughts and prove they're conscious.
Turing himself said that assuming other people can think is just a polite convention.
It's a polite convention.
Yeah.
You can't build a legal framework on a polite convention.
Right.
And that's the challenge. Places like the Harvard Patriot Center point out. Law demands precision and clarity. Our everyday idea of AI based on thinking just falls apart under that kind of scrutiny.
Mm-hmm.
If a regulator tries to base a law on whether a machine is conscious, how do you even begin to verify that?
So the whole argument has to shift. It's not about regulating the nature of the machine.
It's about regulating the consequences of what it does.
The output.
Exactly. The consensus in governance is moving away from defining AI as a thinking thing and toward focusing on the measurable real-world risks of algorithmic decision-making. That's something you can actually define, audit, and regulate.
That's a perfect transition from philosophical debates to practical capabilities. Which brings us to the 4 theoretical types of AI, classified by what they can do.
Right. It's a ladder of complexity. It's a path from simple reaction all the way up to, well, hypothetical consciousness.
So this classification helps us see the evolution of AI.
It does. It goes from reactive machines at the bottom, then up to limited memory, then theory of mind, and finally the most complex stage, self-aware AI.
Okay, let's start at the base level. Type 1, reactive machines.
Reactive machines are the simplest form. They operate only on what's happening right now. They see the world, and they react based on a very narrow set of tasks. The key thing is they can't store past experiences. They don't form memories that influence what they do next. Their entire world is the present moment.
What's the classic example of a reactive AI that people often think was more complex than it was?
IBM's Deep Blue, the chess machine.
Right, that beat Kasparov in '97.
Yes. When it beat Garry Kasparov, it was this incredible feat of computation, but it was purely reactive. It could analyze hundreds of millions of moves a second to find the best one right now, but it had no memory of past games, no concept of winning a tournament, no identity. It was a calculating machine executing a strategy, not a learning system adapting over time.
But reactive AI is still useful today, right?
Oh, absolutely. In advanced web search engines, in simple, real-time traffic management systems, it's still a workhorse.
Which brings us to the next step up, type 2. And this is the type of AI that we are all interacting with every single day.
This is limited memory AI. This is where we live.
Okay.
These are systems that can store and use past data, past experience, for a limited time to get better at what they do. This AI learns from experience, it sees patterns, and it adjusts what it does next. The deep learning revolution of the last decade is what made this possible at scale.
So when my Netflix feed suggests a show based on my viewing history?
That's limited memory AI. It's drawing patterns from your history and the history of millions of other people.
And this is the critical point I want to make sure everyone gets. Generative AI, including the big large language models like ChatGPT, they fall under this category.
They fall squarely under limited memory AI.
Yes. But the output is so human. It's so articulate. It feels like it must be conscious. Is that just a very clever illusion?
It is a statistical phenomenon, but one operating at such a vast scale that it creates the impression of awareness. The underlying mechanic is actually simpler than you'd think. The algorithm is just identifying the statistically most likely word or token to come next in a sentence.
Based on everything it's been trained on.
Everything it's been trained on plus your specific prompt. It can generate novel, original outputs, absolutely, but it has no genuine self-awareness, no desires, no consciousness. It is a brilliant, brilliant mimic.
That is such a key distinction, and it leads us to type 3, which is the conceptual next step. The one researcher sees the gateway to true general intelligence.
Theory of mind AI.
Right.
And the theory of mind is way more complex than just matching patterns. This next stage of AI wouldn't just process data. It would be able to understand and model the emotions, intentions, and mental states of other beings.
So it's about developing real social intelligence, understanding that I have beliefs and hopes that are different from its own.
Exactly.
So where are we with that? How close are we?
Still undeveloped. We're very far from successful. We do not have true theory of mind AI. However,
Okay.
the advances in LLMs are starting to simulate empathy with uncanny effectiveness. They can acknowledge a compliment. They can respond with sympathy if you're frustrated. They can tailor their language based on your inferred mood. It definitely hints at a future of emotionally aware systems.
You know, I saw some fascinating research on this, about how quickly we humans start to treat these systems like people, even when we know they're just algorithms.
That research is so important. There's an NSF grant for a study by Jamie Banks looking at exactly that, how our language and social cognition shapes how we see these AI companions. They're trying to understand the subjective experience of seeing an AI companion as someone.
Wow.
And how that labeling, the anthropomorphizing, affects the user. We're just hardwired to see personality in things, and that's a huge factor in why LLMs seem so intelligent.
Which brings us to the final, most ambitious stage, the one that's usually just pure science fiction, type 4.
Self-aware AI. This is the mountaintop. A machine with human-level consciousness, self-awareness, needs, desires, emotions.
This is where we get into things like artificial superintelligence, or ASI.
Yes, intelligence that vastly exceeds even the greatest human minds. And concepts like the technological singularity, where machine intelligence just accelerates beyond our ability to control or even understand it.
But we're not there yet. What's the main thing holding us back? If we have the data and the computing power, what's the obstacle?
It's primarily our own lack of understanding about consciousness itself, and then the limits of our current hardware and algorithms. We still don't fully grasp how the human brain's processes memory, learning, decision-making translate into the subjective feeling of being alive. So replicating that in a machine remains, for now, out of reach. We've gotten really good at replicating the behavior of intelligence, but not the why of consciousness.
Okay, so let's move from those philosophical types to the technical nuts and bolts. Let's get really clear on the acronyms. AI, machine learning, ML, and deep learning, DL. What is the exact relationship between those three terms?
It's a hierarchy. Think of it like Russian nesting dolls. AI is the biggest doll, the broadest term for any computational system that does tasks we associate with human intelligence.
Okay.
Inside that doll is a smaller one, machine learning, or ML. That's a subset of AI focused on algorithms that learn from data to get better at a task without being explicitly programmed for every step.
And inside that one
is the smallest doll, deep learning, or DL. That's a specific, very powerful type of machine learning that uses artificial neural networks with many layers to process data.
Got it. So deep learning is a way to do machine learning, which is a way to achieve AI. Let's dive into the main ways we actually train these things, the main machine learning paradigms.
Right. We usually classify them based on the kind of training data they use. The first, and maybe most common, is supervised learning.
So if it's supervised, is it like the model is learning from a giant answer key?
That's a perfect analogy. The training data is explicitly labeled with the correct answers. The model's job is to learn how to map the inputs, say an image, to the known output, say the label cat. It just keeps trying and minimizing its mistakes.
And this is what we use for things like spam detection or image recognition.
Yes, for classification tasks, predicting a category, or for regression tasks where you're trying to deduce a number, like predicting a house price.
And then you have the opposite of that, unsupervised learning.
Right, no answer key here. The model gets a bunch of unlabeled data and has to find the structure on its own. It has to identify patterns, relationships, clusters within the data.
So it might group similar customers together for marketing, for example.
Exactly. That's a classic clustering task.
The third paradigm seems like the most dynamic one because it involves an agent actually doing things.
Reinforcement learning, or RL. This is fundamentally different. It trains an agent through trial and error, using feedback rewards and punishments from its environment. The agent learns a strategy, a policy, that maximizes its total reward over time.
It's the closest thing AI has to how a child learns to ride a bike.
It is, but it involves this very delicate balancing act.
Between what?
Between exploration, trying new, maybe risky things to see if there's a better way, and exploitation, sticking with what you already know works well.
Too much exploring and you never get good at anything. Too much exploiting and you might miss a genius new strategy.
Precisely. This is the technique behind the AIs that master games, and it's also crucial for robotics and other complex control systems.
And a really important modern version of this is used to fine-tune large language models, right? RLHF.
Reinforcement learning from human feedback. Absolutely. This is a post-training phase. Human reviewers look at the model's outputs, and they score them for things like helpfulness, truthfulness, and safety.
And the model learns to produce more of the stuff that gets a high score.
Exactly. It refines its policy to align its behavior more closely with human values, or at least the values of the human reviewers who are providing the feedback.
That shows how these different learning types all intersect. What about taking what you learned solving one problem and using it to solve a new one?
That's transfer learning. It's incredibly efficient. You take a model that's been trained on a massive general data set like identifying millions of objects and photos, and you transfer that knowledge, those learned features, to a new, more specific problem.
Like identifying tumors in medical scans.
Right. It dramatically speeds up training and means you don't need a gigantic labeled data set for every single niche problem.
Okay, now for the engine behind the current AI boom, deep learning. What makes it fundamentally different from older machine learning methods?
It's the structure and the scale. Deep learning uses artificial neural networks, which are loosely inspired by the brain. But the key is that they have multiple layers, at least 2 hidden layers between the input and the output.
And those extra layers let it learn more complex things.
They let the network progressively extract higher level, more abstract features from the raw data.
Can you walk me through an example of that?
Sure. Take image processing with a convolutional neural network, or CNN. You feed it an image. The very first layers might just identify simple things like horizontal and vertical edges or little curves.
The basic building blocks?
The absolute basics. Then the next layers combine those edges to detect more complex patterns, like textures or corners. The layers after that combine those patterns to recognize parts of objects, like an eye or a wheel. And finally, the top layers put all those parts together to identify a whole object, a car, a person, a cat.
So it builds complexity automatically, layer by layer, instead of needing a human to program in what an eye looks like.
That's the power shift. But it's crucial to remember that the big boom in deep learning in the 2010s wasn't because of some brand new theory.
Right, the ideas have been around for decades, so why did it suddenly take off?
2 big things came together. First, a massive increase in computing power, specifically from using GPUs or graphics cards, which are fantastic at the kind of parallel math these networks require.
And the second thing?
Data. The availability of huge, organized data sets to train on, like the ImageNet database. The compute power and the data finally caught up with the theory.
Okay, let's focus now on the tech that's generating all the excitement right now. Generative AI and large language models?
Right. Generative AI, or Gen AI, is all about using these deep neural networks to create new content, text, images, code, music. But the key architectural breakthrough here is the transformer.
I hear that word constantly. What is a transformer and what does it do that older models couldn't?
Older models, like recurrent neural networks, had to process text one word at a time, which created a bottleneck. The transformer architecture, which came out in 2017, completely changed the game with its defining feature. The attention mechanism.
Okay, let's break that down. Why is attention the magic ingredient?
The attention mechanism lets the model weigh the importance of all the different words in the input text when it's processing any single word. So if you say, the banker went to the river and saw a fish, he took a loan, the model uses attention to figure out that he probably refers to the banker, not the river or a fish.
Yeah, and crucially, it does this by looking at the whole sentence at once, not word by word.
Exactly. You can see the relationships between words across huge distances in the text, which allows for much deeper context and much longer, more coherent writing. That's how generative pre-trained transformers, or GPTs, work. They just keep predicting the most statistically likely next word, guided by that attention mechanism.
So we pre-train them on whole internet, basically, and then we refine them with that RLHF process to make them helpful and safe. And now we're seeing models that can handle more than just text.
Multimodal models, like Google's Gemini or Microsoft's Copilot, they're the next step. They can process images, video, sound, and text all at the same time. They can draw connections between what's in a photo and what's in your text prompt, giving them a much richer understanding of the world.
Now, let's zoom out even further to the core computational techniques that make all of this possible. Let's start with logic.
Formal logic is still really important, especially in older symbolic AI systems. You have propositional logic, which deals with simple true-false statements, and predicate logic, which is more complex and can handle objects and relationships like every X is a Y.
So these logic-based systems draw conclusions from a set of predefined rules.
Correct. But the big problem with pure logic systems is that the real world is messy and uncertain. It's almost impossible to write down all the rules for a complex environment.
Which is why we need tools to handle that uncertainty. And that brings us to probabilistic methods.
Right. Most interesting AI problems involve incomplete or uncertain information. So researchers use tools from probability theory, things like Bayesian networks, which let systems reason and learn by calculating probabilities, or Markov decision processes, which help model decision-making over time when outcomes aren't certain.
And game theory fits in here too.
Game theory is crucial for describing the optimal behavior of multiple agents interacting with each other. It's essential for competitive environments.
And the third set of these fundamental techniques is search and optimization. Because at the end of the day, so much of AI is just about searching for the best possible answer.
Optimization is the absolute core of training a model. And the key technique used to train pretty much all modern deep neural networks is gradient descent.
This is one of those terms that sounds intimidating, but the concept is pretty simple, right? Can you walk us through the analogy?
Sure. Imagine you're standing on a mountainside in thick fog, and your goal is to get to the lowest point in the valley.
Okay.
The elevation is the model's error, or loss. You want to get that error as low as possible. Since you can't see, all you can do is feel the slope of the ground right where you're standing.
Right.
Gradient descent is just the process of taking a small step in the direction of the steepest downward slope. Then you stop, feel the slope again, and take another small step down. You just repeat that until the ground is flat. You've found the bottom.
And those little steps, those adjustments to the network, are handled by the backpropagation algorithm.
That's exactly right. Backpropagation is the engine that efficiently calculates which way is downhill, the gradient, and sends that error signal backward through all the layers of the network, telling every single connection how to adjust itself just a tiny bit to reduce the overall error.
And beyond that, we also have search methods inspired by nature.
Yes, things like evolutionary computation, where you create a population of solutions and let them mutate and recombine, with only the fittest surviving to the next generation. And swarm intelligence algorithms.
Like ant colonies.
Exactly. Ant colony optimization is inspired by how ants find the shortest path to a food source. These are all powerful ways to solve really complex optimization problems.
It's amazing how much is going on under the hood. Okay, now that we understand the definitions and the engines, let's talk about the impact. Where is all this technology actually being used right now? Let's start with a really critical one. Health and medicine.
AI is completely changing healthcare by enabling data-driven decisions everywhere. In diagnostics, you have deep learning tools analyzing medical images, X-rays, CT scans, and they're often reaching accuracy levels that are equal to or even better than human specialists.
But the truly mind-blowing progress has been in drug discovery. Tell me about AlphaFold 2.
AlphaFold 2 is a landmark achievement. It can accurately predict the 3D structure of a protein in just a few hours, a task that used to take months or years of lab work.
And a protein's shape determines what it does, so this is a huge deal for understanding diseases.
It's a game changer. It dramatically speeds up our ability to understand how diseases work and how to design drugs to fight them.
And the sources had a specific example with Parkinson's disease.
Yes. Machine learning was used to screen millions of chemical compounds to find ones that might block the protein clumping associated with Parkinson's. That initial screening process was sped up tenfold, and it reduced the cost of that early-stage research by a factor of 1,000.
That's not a small improvement. That changes the entire economic model of biomedical research.
It does. And beyond individual health, AI is also being used for public health and disaster management.
How so?
By analyzing real-time data from GPS, traffic cameras, social media, AI systems can predict where bottlenecks will form during an evacuation or which areas need resources most urgently after a disaster. It helps officials make faster, better decisions that can save lives.
Okay, next up, finance. This industry was one of the earliest and most aggressive adopters of AI.
And for good reason. Money and data are a natural fit. AI is everywhere in finance now, from trading algorithms and robot advisors to the highest stakes applications, large-scale fraud detection.
Let's spend some time on that, specifically on using data-centric AI, or DCAI, to improve Medicare fraud detection. This is where billions of our tax dollars are on the line.
This comes from a really crucial study on Medicare claims data from CMS. For a long time, the machine learning world was obsessed with the model. Everyone was trying to build a slightly better algorithm.
But data-centric AI flips that script.
It completely flips it. DCAI says, hey, in the real world, 80% of the work is just getting your data clean and ready. The quality of your input data is often way more important than which specific algorithm you choose.
So how did this study apply that DCAI idea to find more fraud?
The researchers focused intensely on enriching the data. They took the existing Medicare fraud data sets and they engineered dozens of new features, up to 58 new data points for each claim.
And these weren't just random data points.
No, they were complex, aggregated predictors, things that describe the provider's history, the patient's history, the claim's context. They were building a much richer story for the AI to learn from. They call these the aggregated enriched data sets.
And what was the result? Did focusing on the data actually work better?
It was a complete validation of the DCAI approach. The aggregated enriched data sets consistently and significantly improve the model's performance. The AUC score, which is a key metric for how well a model can classify things, went up meaningfully. Those new features provided a measurable lift.
What I found fascinating, though, was that they also had to change how they tested the model because the standard methods were giving them results that were just too good to be true.
This is such a critical and advanced insight. They found that the standard testing method, K-fold cross-validation, was sometimes giving them an AUC of 0.99, near perfect.
Yeah.
But it was unreliable because of something called target leakage.
Okay, what is target leakage?
It's when information about the thing you're trying to predict, in this case, fraud, accidentally leaks into your training data. For example, a single fraudulent doctor might submit dozens of claims. If the standard testing method puts some of those claims in the training set and some in the test set, the model can just learn to recognize that doctor's pattern. It's basically cheating.
So it looks perfect in the lab, but would fail in the real world when it sees a new doctor for the first time.
Exactly. So they fixed this by using an improved technique called K-fold by NPI, where NPI is the provider's ID number. This made sure that all claims from a single doctor were either all in the training set or all in the test set, never split.
And that gave them a more realistic score.
A much more realistic maximum AUC of around 0.95. It's a powerful reminder that how you test your model is just as important as how you build it, especially when the stakes are this high.
Absolutely. Okay, moving to a slightly lighter topic. Games. Games have always been the proving ground for AI.
They've been the benchmark since the 1950s. The milestones are legendary. Deep Blue beating Kasparov in chess, IBM Watson on Jeopardy, and then AlphaGo beating the world's best Go player.
And these achievements just keep getting more complex.
They do. In 2019, DeepMind's AlphaStar reached Grandmaster level in StarCraft 2. That was a huge deal. Because StarCraft is a game of incomplete information, you can't see the whole map. It requires long-term planning and reacting in real time. It's much messier than chess.
And the models are getting more general, too, moving beyond just one game.
That's the real shift toward general intelligence. You have models like Mu0, which learns to play chess, Go, and Atari games without even being told the rules. It just figures it out by playing against itself.
That's amazing.
Right.
What about in more abstract fields like mathematics?
LLMs are being used for math, but it's tricky. Because they're probabilistic. They're prone to making mistakes, to those hallucinations. But researchers found a key insight.
What's that?
Their performance gets way better when you train them, not just to give you the final answer, but to produce the correct reasoning steps.
So you have to teach it to show its work, just like in school.
Exactly. It forces the model into a more logical, deductive process. And beyond LLMs, you have specialized models like alpha geometry that are solving complex geometry problems at a really high level.
And finally, what about in our everyday lives? AI is everywhere now, often in ways we don't even see.
In e-commerce, it's doing real-time fraud prevention on your credit card transactions. Social media platforms use it to personalize your feed and to moderate content at a scale no human team could ever manage.
And the sources point out it's even entering very intimate parts of our lives, which really highlights the dual-use nature of the tech.
It's a necessary point. AI is in fertility trackers and AI companion apps like Replica. But the dark side of that same technology is the epidemic of non-consensual deepfake pornography. The technology itself is neutral. Its impact depends entirely on how it's used.
Speaking of impact, we've talked about all the good it can do. But that power comes at a cost. Let's shift to the critical challenges, starting with one that's often ignored: the massive environmental impact.
The energy consumption of modern AI is frankly prodigious.
Yeah.
It's a real and growing crisis. The International Energy Agency estimated that the power demand just from AI and crypto might double by 2026.
Double. What does that even look like in real terms?
That increase alone would be equal to the total electricity used by the entire country of Japan.
That's a staggering number. Our power grids can barely handle the load now.
And this surge in demand is currently driving a growth in fossil fuel use because we need the power now. A single complex search on ChatGPT uses about 10 times the energy of a standard Google search. This is why you're seeing big tech firms in a frantic race for massive, constant power sources.
Which explains all these deals for nuclear power plants we're suddenly hearing about.
Exactly. Amazon bought a nuclear-powered data center for $650 million. Microsoft made a deal to potentially reopen 3 Mile Island. They need that dense 247 power to train and run these huge models.
But these deals are hitting some regulatory roadblocks.
They are. The Federal Energy Regulatory Commission, FERC, rejected one big proposal, citing the huge burden on the public electricity grid and concerns that the costs would be shifted onto regular households. The environmental footprint of this technology is growing incredibly fast, and regulators are starting to pay very close attention.
The next huge challenge, and this one gets to the very core of social justice, is bias and fairness.
This is the core ethical problem. Machine learning models are not objective. They're a reflection of the data we train them on. If you train them on biased historical data, they will produce biased and discriminatory outcomes.
And we have some really painful, high-profile examples of this happening.
The Google Photos incident from 2015 is a classic. Its image labeling AI mistakenly identified Black users as gorillas.
And this was because the training data was skewed.
It was a sample size disparity. This system just hadn't seen enough pictures of Black people to learn to classify them correctly. And their fix was to just block the system from ever using the label gorilla, which shows how hard it is to patch these deep-seated data problems.
And then there's the COMPAS system, used in the justice system, which shows how bias can creep in even when you try to prevent it.
COMPAS is a tool used to predict the risk of a defendant reoffending. The system was intentionally blinded to race. But an investigation by ProPublica found it was still profoundly biased.
How so?
The type of error it made was racially skewed. It consistently produced false positives for Black defendants, saying they were high risk when they weren't. And it produced false negatives for white defendants, saying they were low risk when they actually went on to reoffend.
So fairness through blindness just doesn't work. Removing the race feature isn't enough.
Not when race correlates so strongly with other features in the data, like zip code or income level. This leads to a critical insight. ML is descriptive, not prescriptive. If you train a model on a history of racist decisions, it will learn to predict racist outcomes. It's not well suited for areas where we want the future to be less biased than the past.
Which leads us directly to the next challenge: lack of transparency, the black box problem. If we don't know how a machine made a decision, how can we fix it or hold it accountable?
Right. Many of these deep neural networks are so complex, with millions of interacting parameters, that even their own designers can't fully explain why they reached a specific conclusion. This creates a huge trust deficit, especially in high-stakes fields like medicine.
The sources had some almost comical but terrifying examples of this.
There was a skin cancer detection system that performed really well in tests. But when they dug into it, they found it had learned to associate the presence of a ruler in the photo with cancer.
Because doctors use rulers to measure moles in pictures of malignancy.
Exactly. It learned to spot the ruler, not the cancer. Another system classified asthma patients as being at low risk of dying from pneumonia.
Which is the opposite of reality.
Completely. But in the training data, asthmatics get much more intensive care, so they were statistically less likely to die. The AI confused the result, getting more care with the cause. It confused correlation with causation.
This opacity is why you see concepts like a right to an explanation popping up in regulations like the EU's GDPR.
Yes. If an algorithm denies you a loan, you have a right to know why. Regulators are basically saying if you can't solve the black box problem, then maybe these tools shouldn't be used in critical areas where they can do real harm.
Okay, finally, let's look at the big picture. The massive societal risks and governance questions. Starting with jobs.
Technological unemployment is a huge concern. And what's different this time is that AI is coming for white-collar, knowledge worker jobs. The CEO of Ford predicted AI could replace half of all U.S. white-collar workers.
It's not just factory jobs anymore. It's paralegals, analysts, designers. The Chinese video game industry reportedly lost 70% of its illustrator jobs to generative AI.
And this disruption is happening at the same time AI is giving incredibly powerful tools to bad actors. It enables widespread surveillance by authoritarian governments and the ability to target propaganda with terrifying precision.
And then there's the ultimate risk, weaponization.
The development of lethal autonomous weapons, or Law W's drones, that can select and engage human targets without a human in the loop, is a major global concern. Some sources even argue that AI could be a weapon of mass destruction, noting that it can be used to design tens of thousands of new toxic chemical compounds in just a few hours.
This combination of incredible power and incredible risk is why we're seeing this explosion in global regulation.
It's an exponential curve. The number of AI-related laws passed globally went from just 1 in 2016 to 37 in 2022. You have the EU's AI Act, the Council of Europe's Treaty on AI and Human Rights. The world is scrambling to put guardrails in place.
So we've gone from a few guys brainstorming in a summer seminar in 1956 to a full-blown global regulatory race just 70 years later.
And that journey really tells the whole story of the field. It started with that beautiful, abstract idea at Dartmouth that you could simulate intelligence. And in many ways, we've succeeded through the power of pattern recognition and massive data, but we're still grappling with the exact same fundamental issues. How to define human values, how to manage scarce resources like energy, and how to deal with the biases that we ourselves build into these systems.
And here's where it gets really, really interesting. When you look at that gap between the original goals and what we can do now. We talked a little about Moravec's paradox.
Right, the old idea from the 80s that for AI, the hard things like chess or calculus were easy, but the easy things like walking or recognizing a face were almost impossible.
It was a huge roadblock for that early, logic-based symbolic AI. Philosophers argued that human expertise relies on this unconscious feel for a situation that you just can't program with rules.
And they were largely right. That's why the field moved away from pure symbolic AI.
But today's deep learning has basically flipped Moravec's paradox on its head. Modern AI has mastered many of those instinctive tasks that the old AI failed at, recognizing faces, translating languages, driving cars.
It has. But look at what we still can't do. We still can't really define consciousness. We still can't guarantee fairness when we're using biased historical data. And we still can't always explain why the system made the choice it did. We've kind of swapped one set of hard problems for another, and true general intelligence is still the ultimate elusive goal.
Which leaves us with a final provocative thought for you to take away. If current AI systems are designed to make predictions based entirely on past data, and we know those predictions, when they're used in medicine or finance or policing, can reinforce historical biases, what fundamental shift has to happen in how we collect and label our data to make sure the AI we build creates the future we hope for, and not just a perfect replica of the one we already had? Should we be regulating the definition of AI or the real-world consequences of the algorithmic decisions themselves?